Hello and welcome to a new video in a course on calculus. In this video, I plan to cover the definition of bounded and monotone sequences, give some examples, and present a theorem that discusses convergence of monotone bounded sequences. So let us start by defining what bounded sequences are. So I remind you, sequences are these list of numbers that actually allow repetition and where order matters. So let's take an example before. So as a motivation for this definition, let's take just an example here. So if you look at the sequence 1 over n, right? So if we take an to be 1 over n. Right, so if you look at this sequence, you notice that for every index n, this sequence is positive, right? So whatever the index is, the element of the sequence appearing in the sequence is positive. So all of these terms are bounded below by 0. On the other hand, if you look at 1 over n, 1 over n is like 1 divided by a number. When you divide like 1 by a number bigger than or equal to 1, you get a number less than or equal to 1, right? So an is also bounded above by 1. So this is the notion of boundedness, and in more details, or in more in a more formal way, here's how we define it. So a sequence, let's say an, is said to be bounded from above by a number m, right? It's bounded by m if an is less than or equal to m for every, let me just write, for every n. So in other words, so this inequality should hold for every n. I stress that the for every n is important here, in which case we call m an upper bound, right? So similarly, we say a sequence, and we just given an example. For this one, an equals to 1 over n is bounded above by 1, right? So this is the upper bound in this case. So a sequence is said to be bounded from below. So let's say a sequence an is said to be bounded from below if, let's say by a number n, if an is bigger than or equal to n for every n, right? And we call n a lower bound. What is an example of this? Well, an, which is equal to 1 over n, is also an example, because we know that this is bigger than 0 for every n, right? So this is a lower bound. So this sequence is lower bounded by 0. So this is the definition of a sequence that is bounded from below and above, and the definition of upper and lower bounds. Now, a sequence that is both bounded from above and below is called a bounded sequence. So a sequence is bounded, sequence an is bounded if it's both bounded from above and below. So i.e., in other words, there exists a number m and a number n such that an is between n and m for every n, right? And an example of this is also the sequence 1 over n, because you see 1 over n is less than 1 and it's bigger than 0 for every n. So an, which is equal to 1 over n, is just an example of a bounded sequence. So why are bounded sequences important? We're gonna take more examples, but let me just tell you why are these important. Well, the reason these are important is that usually when I ask you to compute a limit of a sequence, the first question that you ask yourself is whether or not the limit exists. Like you ask first of all, when I tell you compute the limit of an for a given an, the first question that you should ask yourself is whether the sequence is convergent or divergent. Because if the sequence is divergent, then either the limit doesn't exist or the limit will be infinity, right? However, it would be nice to tell which sequences are convergent and which sequences are like divergent in order to know what to expect when you want to compute a limit, right? So so sometimes you get a question, determine whether or not the sequence is convergent, in which case you don't need to compute the limit to prove that. You just need to prove whether the limit exists or not, and the bounded monotone sequence theorem is going to be an important tool that will help you with that. So that's a reason, one reason why bounded sequences are important. This is the definition of bounded sequences, and let us define now what a monotone sequence is. So what is a monotone sequence, right? So here's the first definition. So we say a sequence an is increasing. Another word for that, monotone increasing. If an is less than an plus 1 for every n. And as you see, this is equivalent to saying that the difference of an plus 1 and an, if you subtract an plus 1 from an, you want this to be positive, because if you bring this to the other side, this is equivalent to requiring that an plus 1 minus an is positive. And usually, looking at the difference of these and trying to prove that it's positive, it's easier, like when you attempt to prove that some sequences are monotone or monotone increasing. It's easier to prove this rather than trying to prove this inequality directly. Right, so similarly, we have the notion of decreasing sequences, but before that, let me just state that there's a kind of a similar definition to this thing, which is that you say a sequence is non-decreasing, right? So you have the notion of increasing and you have the notion of non-decreasing. You say a sequence is non-decreasing if the same thing happens, but except instead of the strict less than or equal, less than sign, you have the less than or equal sign, right? So here you will have the bigger than or equal sign. So so a non-decreasing sequence is when you allow repetition among the elements of the sequence, and the increasing or strictly increasing means you don't allow repetition. Okay. So there's a similar definition, which is a sequence an is said to be decreasing if you have an plus 1 is less than an for every n. So I'm gonna use this notation. So this means for every, right? So if you look at this, it's kind of the opposite of this definition over here. So you kind of flip the inequality and you call the sequence decreasing. So as you see, you can define this equivalently as you want the an plus 1 minus an to be negative. So often when I tell you prove a sequence is decreasing or increasing, it might be easier to look at the difference and try to prove it negative and hence get a decreasing sequence, or prove it positive and get a increasing sequence. Similarly, just as in the case of the increasing sequence, we have a kind of similar definition, which is when we ask for non-increasing, or we use the terminology of non-increasing sequence. Non-increasing means the same thing except that we allow repetition. So we allow that this is less than or equal, and in this case this is going to be less than or equal. So this is the kind of similar definition, and a sequence is monotone if it's either, right? If it's either increasing or decreasing. We call a sequence to be monotone. And again, why is this important? But before that, before we tell why this is important, let's take a few examples here of monotone sequences. So let's take a few examples. So the first example is an equals to n, right? If you list the elements of this sequence, at index 1 you have 1, at index 2 you have 2, and then 3, and then 4, and so on, because this is n equals 1, this is n equals 2, this is n equals 3, and so on. And if you look at this sequence, right, every time like you go to a higher index, you see that the terms are getting bigger. So it seems like this sequence is increasing, right? So how would you show that? Well, you want to show that an plus 1 minus an is positive, because remember, this is how we defined an increasing sequence. We either prove that this inequality holds, or we prove that the difference is positive. But let us practice using the difference definition. So you look at the difference of these. What is an plus 1? So an plus 1, instead of n, you're gonna plug in n plus 1. So you have n plus 1, and an is just n, so this is negative n, and this is what? This is just 1, which is positive. And since it's positive, you see that the sequence is what is actually increasing. This implies an is increasing. All right. So this is the first example. Let's take another example here. So let's take a non-example. Let's take an example of a sequence that is not monotone, right? So what is an example of a sequence that is not monotone? So if you take an to be negative 1 to the n, right? If you look at this, if you list a few elements of it, n equals 1, this is negative 1 because it's negative 1 to the power 1. And then n equals 2, it's negative 1 squared, and hence it's plus 1. And then if you evaluate this at n equals 3, this will be negative 1, and then plus 1. So it's the alternating sequence, right? So if I ask you, is this sequence monotone? You see, from here to here, it's decreasing because it decreased from plus 1 to minus 1. From here to here, it's increasing because it increased from negative 1 to 1. And remember, this is very important. The property of increasing or decreasing requires this inequality to hold for every n, like for every index. However, if you look at this, you try a few indices and you see that this is not true. Like, it's not true that there's one inequality happening always, right? So this is not monotone. Okay. It might be good to take one more example. So let's take an example, an equals to 1 over n. What is this? Well, this sequence is decreasing. Why is that? Well, because if you list a few elements of it, you have 1, 1 over 2, 1 over 3, and so on. You see that as you increase the index, you're dividing by a bigger number, and hence as you go to bigger indices, the element is getting smaller. And how would you prove this mathematically? Well, you know that n is less than n plus 1, right? So when you take the reciprocal of these, you're going to have 1 over n is bigger than 1 over n plus 1. You change the comparison sign, and this on the right is an plus 1, and this on the left is an, and this is just the definition of what decreasing sequence is. So this is decreasing. Remember, this is how we define a decreasing sequence. It's when an plus 1 is less than an for every n. This is important. So this is for every n. Okay? So these are examples of monotone sequences. And now that we defined monotone sequences and bounded sequences, we're ready to talk about our new tool in deciding whether or not a sequence is convergent or divergent. So here's the theorem in a very simpler, in the most simple words. A sequence that is both monotone and bounded, it's convergent. Okay? So what does it mean that a sequence it converges? It means that the limit exists, right? It means that when you compute the limit will be a number. It won't be infinity, or as in the case of -1 to the n, it won't be the case that the limit doesn't exist, right? So the limit exists and it's equal to a number. So so a sequence that is both bounded and monotone is convergent. So the proof of this theorem is not hard, but it's kind of uses some tools that we won't cover in this course. So you might see this in an analysis course or something. So let us take an example, but before we do that, let me stress something here that is very important. We're not saying that if a sequence is convergent, then it's bounded and monotone. And we're going to give an example where this is not the case. So what we're saying, if this left-hand side happens, right? If this is true, then this is true, right? Please be careful. It's not the other way around. If something happened, if the monotonicity and the boundedness happened, then convergence happens. So let's take a few examples of this, and we're gonna then give a non-example of the converse. So let's take a few examples of the applications of this theorem. So if we take the sequence an equals to 1 over n, we proved before that the limit of an as n tends to infinity is equal to 0. Now say, so this means that the sequence is convergent. So we know that, right? But say I didn't ask you to compute the limit. I only asked you to decide whether or not the sequence is convergent, so you don't need to compute the limit. So how would you know if the sequence is convergent or not? So the very important tool that we just learned is try to prove the sequence is bounded and monotone, and you will get convergence. Now this sequence, this theorem can be stated in two different ways, and let me just stress this because this is important. The first statement is that if it is bounded above, if you have a sequence that is bounded above and increasing, then it's convergent, right? The second part is if it's bounded below and decreasing, then it's also convergent. And the other one is that if it's monotone, if it's either increasing or decreasing and not bounded, then it's divergent. Okay. So, so we're gonna give examples of the three cases, and we're gonna see how important this theorem is in deciding whether whether a sequence is convergent or not. So if you look at an equals to 1 over n, we know that the limit of it is 0, right? But how would we know if it's convergent if we didn't want to compute the limit? Well, we know that an is bounded below by 0 because we know that 1 over n is always positive, right? Okay, so the sequence is bounded below, and so if it suffices to prove that the sequence is decreasing to get that the sequence is convergent, because remember, this is the version of the theorem we're using. It's bounded below and it's decreasing, and hence it's convergent. So why is it decreasing? Because remember, we just proved this, because n is less than n plus 1 for every n, and thus 1 over n is bigger than 1 over n plus 1 for every n, and this is just an plus 1, and this is just an for every n. This is happening, and thus this is the definition of decreasing sequence. Thus this sequence is decreasing. Okay, so we get convergence. So an is convergent by the monotone. This is called the monotone sequence theorem. By the monotone sequence theorem. So so we got convergence, but let me just tell you intuitively why this is true. Well, you have a sequence, right? And it's always bigger than 0, and it's always decreasing, right? So since it's decreasing and it's bigger than 0, right? So intuitively, it should stop somewhere at some point and give you an answer, right? So let's take another example, and the question is this sequence convergent or not? Now you can compute the limit from just as we did in the last videos. You can compute the limit of this, because the limit respects the arithmetic operations. This will be the limit of 1, which is 1, minus the limit of 1 over n, which is 0. So this will be 1 minus 0, which is just 1. So you know that this sequence is convergent. You do know that, right? So so since this is true, you expect that the monotone theorem will give you the true result. So you could have computed the limit and concluded convergence, or you can use the monotone theorem to tell you that the sequence is indeed convergent. So why is that so? Well, if you look at an, right, an is equal to 1 minus 1 over n, and this is 1 minus a number, right? So this is 1 minus a positive number. So this is less than 1, right? Because so every time you're taking 1 and you're removing something from it, you'll be less than 1, right? So let us so this is what we have, right? So we have an upper bound. So we have an upper bound that is 1, meaning an is bounded above, right? So an is bounded above by 1, and so it suffices to prove, so you have an always loses to 1, so it suffices to prove that an is increasing to get convergence, because remember, this is what the theorem is telling us. If it's bounded above and it's increasing, hence it's convergent. So so let us see why is it increasing. Well, if you look at so we said that one way is to use the inequality, and the other way is to look at the difference. So let's look at the difference of an plus 1 and an. This is so if you put here n plus 1 instead of n, you have 1 minus 1 over n plus 1, and then you're subtracting 1 minus 1 over n, which is an, right? And what is that? This is just the 1 and the 1 will go, and you'll be left with 1 over n minus 1 over n plus 1. Now, if you look at this, you actually know that this is positive, for every n. But why is that true? Well, because n is less than, just as we agreed, like argued before, n is less than n plus 1, and hence 1 over n is bigger than 1 over n plus 1, and hence 1 over n minus 1 over n plus 1 is positive, right? And this is the equivalent way of saying that, so one way is to say that an is less than an plus 1 for every n. So this is one way to prove that a sequence is increasing, and the other way is to look at the difference and prove it's positive, right? So we just proved that the sequence is increasing and it's bounded above, and hence by monotone theorem, monotone sequence theorem, it's convergent. Now here's a warning for you. Here's an important warning for you. If a sequence is bounded above by a number and it's increasing, it doesn't mean that it's gonna converge to that number. So let me give you an example here. So we know that an, for example, equal to 1 minus 1 over n, the sequence that we just discussed. This is less than 1, right? This is less than 1. This thing we know. And because we proved that we agreed that it's bounded above by 1. But it's also, if it's less than 1, it's also less than 2, right? It's also less than 2. So, and this sequence is bounded above by 2, and this sequence is increasing, and thus it's convergent. But this is not enough to say that the limit is 2, right? The limit would not be 2. This is very important for you to keep in mind. The limit is not 2. The limit will be less than 2, less than or equal to 2. That is correct. But the limit is not 2. Okay? I hope this is clear, because if you remember, we just computed the limit and we saw that it is 1, it's not 2. So the monotone sequence theorem, it tells you whether or not the sequence is convergent, but it doesn't tell you what the limit is, right? This is important to keep in mind. So let us take a non-example now, and we're gonna wrap up this video. So a non-example, let's take the sequence an equals to n, right? So if you look at this sequence, you remember, like when we take the limit of this, you see that this is infinity, right? So this is divergent. This sequence an is divergent. But is there a way to see this from the monotone theorem, monotone sequence theorem? Is there a way to see why this is the case? So yes, there is. So you can either prove it using the monotone theorem, or you can prove it using the limit, just as we did. But why is it true using the monotone sequence theorem? Well, the sequence an, if you look at it, it's equal to n. And the n is always less than n plus 1, and n plus 1 is just equal to an plus 1, right? So an is increasing. But if an is increasing, there's a problem here, which is that the sequence is not bounded from above. An is not bounded from above, right? So the sequence is not bounded from above. So so you have a sequence that is increasing, an is increasing, and there is no bound from it from above, and thus this theorem will tell you that divergence will happen. So if it's not bounded and it's monotone, then it should be divergent. Okay? So this is another way to see this. So by the monotone theorem, it's divergent. And since I mentioned a warning for you, let me just prove something real quick for you. So that conveys that the converse of the theorem is not always true. So the theorem that I told you about, it tells you if you have monotone sequence that is also bounded, then you get convergence. But the other way around is not true. Like, you can have convergence, but it need not be monotone or bounded. So for example, if you look at this sequence, okay, so this sequence is convergent. Why is it convergent? Well, because if you remember, we used squeeze theorem, right? We squeezed an, which is, so we squeezed minus 1 to the n between over n, between 1 over n and negative 1 over n, because we mentioned that this is always equal to plus or minus 1. So it's upper bounded by 1 and it's lower bounded by n. And by the monotone, by the squeeze theorem, excuse me, this will be, this is going to 0, this is going to 0, thus this is going to 0, right? Because we know 1 over n goes to 0. Thus, the limit of an as n tends to infinity is equal to 0, and thus the limit exists, right? The limit exists, thus it's convergent. So we know that the sequence is convergent. And we, however, if you look at this sequence, it's not monotone. This sequence is not monotone, because let's write a few terms of the sequence. N equals 1, it's negative 1 to the power 1, so we're plugging the index here. So it's negative 1 to the power 1, which is negative 1 over 1. The next term is negative 1 squared, which is plus 1 over 2. And next we have minus 1 over 3, and next we have plus 1 over 4, and so on. So if you see, the sequence from here to here, it's going from a positive number to a negative number, and hence it's decreasing, right? While from here to here, it's going from a negative number to a positive number, and hence it's increasing. And thus this sequence is not monotone. So this is not monotone. Alright, this is important for you to keep in mind, that this sequence is not monotone, okay? So you can also check that this sequence is bounded, for example. But what I'm trying to say is that the convergence doesn't imply that these two will happen, right? So here we have a convergence sequence, but it's not monotone, okay? So in the next video, we will see how powerful the monotone sequence theorem is by looking at more complicated examples